Hello, welcome back. This is Calculus by Dr. Oz. So we're going to go over another application, another cool application of definite integration. It's finding the volume of the solid. In this case, the solid is generated by revolving the given region about the y-axis. Okay. So and how does the region is built up? So it's you take the curve y equals x cubed over 8, and you take y equals 0, which is the x-axis, and you take the vertical line x equals 4, and you see what the region in between these curves or bounded. So you look at the region bounded by these curves, and let's see what the region looks like quickly, even though you're going to see the details within the video. So this is exactly what the region looks like. So you have the vertical line bounding the right-hand side of the region. You have the x-axis and you have the blue curve over there. So you're talking about this green region, and you're going to revolve this around y-axis. Okay, so essentially y-axis is vertical, so you're going to sort of like revolve this around that y-axis. Let's see what the three-dimensional object looks like quickly. So this is our region bounded by three graphs. Okay, and revolve that around. And what happens is that you have a cylinder outside. Let me just go back here. You have a cylinder outside, and you have the bullet-looking three-dimensional object inside. So you just take that volume of the bullet out. Okay, so you have the cylinder and whatever is left over. Okay, so and then again, I can't show you the inside to you, but I can take a cross section here as I just showed you. That you take the volume of the bullet off, and you have that volume obtained exactly the way I described here. Okay, so also let's go back to the region real quick, and you're gonna take cross sections vertical to the axis of revolution. So and in this case, you're gonna have washers. So for that reason, let me just go back and just show you what the washer method looks like, and then we can start hitting the road. All right, so here is a table that shows the volume of a solid of revolution by the washer method. In the washer method, as I said, we take a slice vertical to the axis of the revolution. In this particular case, the reason why we get a washer, because we have the distance, we have some distance between the slice we pick from the region and the axis of revolution. Okay, so let me just make this picture bigger. In this case, to be able to get down to the volume of the representative washer, you need the outer radius and the inner radius. So outer radius is r, and inner radius is little r in this case. And we took a slice of thickness dx. So that means I should write both radii in terms of x. So if you're able to write down both radii in terms of x, you can go back and write down the volume formula, which is in fact the volume of the outer disk minus the volume of the inner disk. So pi capital R squared minus pi little r squared dx. And x's are ranging in between a and b in this case, so we're integrating from a to b. All right, so let's get started and see what our volume formula looks like. All right, let's take care of this problem. So we have the region bounded by three graphs. One is y equals x cubed over 8. The other one is y equals 0, which is in fact x-axis. And x equals 4 vertical line. And this time we're going to revolve the region about the y-axis. Okay. So first thing is first, please go ahead and check what the region looks like. And obviously, this line and this curve will intersect each other. Okay. So because that's going to be the right end of, or right, like the bound of the right end of the region. Okay. So you can pause the video at any moment and get the visual with your graphing calculator. I'll show you what I got. Here we go. I have the x equals 4 vertical line here. Okay. I have the x-axis, right? I have the x-axis. That was the second thing in the list. And I have the curve. Okay. I have the curve y equals x cubed over 8. Okay. So we have the green region, and we're going to revolve this around y-axis. Okay. And we're going to use the washer method. Okay. So remember, in the washer method, we are taking slices within the region strictly perp to the axis of the revolution. So the slices would look like this, right? Since you take the slices horizontal like this, the thickness for each would be dy. Okay, so that means whatever the integral I'm going to write in the washer technique is going to be dependent on y. Okay, so what happens if you revolve one representative washer here? So you'll have the inner part. Oops. You'll have the inner part, and you have the outer part. Okay. So you exactly get a washer or punctured disc, and the volume of the disc with thickness dy is going to be, so you have the inner radius, right, r, and you have the outer radius, capital R. So volume is going to be pi outer radius squared minus inner radius squared. And since this comes with thickness dy, so I'm going to multiply that as well by dy. Okay. And at this moment, I want to show you the actual three-dimensional object after the revolution. Here we go. This is our region, green region, and we're revolving about the y-axis. Here we go. So we keep revolving, 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 and revolving. Okay, so obviously the inside of that is going to be looking like, you take out this vase-looking or bullet-looking inner part out, and you have the cylinder and the bullet part out. That's a three-dimensional object you have after the revolution. Okay. So what we're going to do is, in fact, to come up with little r and capital R in terms of y. So these guys, r and little r, is going to be in terms of y. Okay. So to do that, let's work through this. Let's get rid of this representative example. Only work with the one that I rolled around. So let's take that slice. Let's say like this slice is y units far from the x-axis. This is the part of the labeling to start with. Okay, so this part is just like y units from the x-axis. Okay, so all I need is the height of, or in this case, the width of the slice, like this part. Okay, so what is this length here? Okay, so in other words, what is this length? But in fact, more than that, I need little r and capital R. Okay, so the very left part of the slice here touches the blue curve. Okay, and I have the equation of that, but I have to write that in terms of y. So right now, the way it's provided to us is y equals x cubed over 8. I'm going to write that as x cubed equals 8y and x equals cubic root of 8y. Okay, I'll just erase this part. I don't need it right now. Okay, so this is the x representation, x equals g of y representation of the same curve. So if you provide me y, I can tell you exactly what this length is. Okay, so in other words, I know exactly what this length is in terms of y. It's in fact cubic root of 8y. Okay. And the capital R, the length of the outer radius, is fixed. No matter what slice you take, that's going to be the distance between the vertical line x equals 4 and the y-axis, and that's going to be 4 all the time. Okay. So this tells me that r, little r, is this guy, and capital R is already 4. Okay. So I'm going to use this formula now to write down the integral. Write down the integral. Pi integral r squared, capital R squared, that's 4 squared, minus cubic root of 8y squared. Okay, that's the little r, right? Little r. So pi times 4 squared minus cubic root of 8y squared times dx is in fact the volume of only one disk, right? But if you integrate it, on dy, and we should determine the limits from the graph. Okay, let me just work on a cleaner version of that. Okay, cleaner version of this graph. There we go. So in this regard, so the y's within the region, the y's, let me just clean this. Y's within the region are changing. Here we go. In between, let's find this top part. In between 0 and something, but we have to find that out. So when x equals 4, that's the intersection point. Y is going to be 4 cubed over 8. That's equal to 8. Okay, so this is y equals 8 horizontal line. So all the y's within the region are ranging in between 0 and 8. Here we go. I'm going to go back and put 0 and 8 here. Okay. So let's simplify this. This is pi integral from 0 to 8, 16 minus. So this is 8y to the power of 1/3 to the power of 2. Okay, that's 8y to the power of 2/3. Okay, 8y to the power of 2/3, and that is also equal to, let me just write down exactly what it is, 8 to the power of 2/3 times y to the power of 2/3. Okay? And 8 to the power of 2/3 is 8 squared, cubic root of 8 squared. Okay, 8 squared is 64, and cubic root of that is 4. Okay? All right, that is equal to pi 0 to 8, integral from 0 to 8, 16 minus 4 y to the power of 2/3 dy. There we go. Let me just write this in a cleaner way. There we go. So right now I'm going to just handle this definite integral. So pi 16y minus 4 times y to the power of 5/3 divided by 5/3 from 0 to 8. And next you're going to plug in the upper limit and then lower limit and subtract from each other. Okay. If you plug in 0, by the way, you get nothing, right? Because y to the power of 5/3 for y equals 0 is 0. 16y is already 0. So this should be pi 128 and 8 to the power of 5 over 3 divided by 5 over 3. If you flip that over, this is 12 over 5. Let's say 8 to the 5 over 3. And if you simplify that, you have 256 pi over 5. By finding a common denominator and simplifying everything, you got 256 pi over 5. And going back to this picture here, I didn't make this see-through, but this is what I'm talking about. The volume of the cylinder minus that bullet shape three-dimensional object subtracted is going to take you to, let me just write it here, volume is going to be 256 pi over 5. All right. I think that takes care of everything, and this is already a long video, so I'm going to stop right here. If you have any questions, comments, or suggestions, please send those to my way, and I'll see you in another video. Bye.